Okay, we're now finally at the point where we can define recurrence, which is the most important of the three properties that we're discussing, right? In irreducibility, periodicity, and recurrence. So this concept is maybe the most involved one of the three. So we're going to spend quite a bit of time with this. This screenshot is coming from the first page of the note on recurrence that I've posted. So, of course we have, Markov chain, which is homogeneous, and kind of the first thing to introduce here is this notion of a hitting time, right? So this is a random variable tx. It's essentially a random time, and if you kind of parse this definition, it should read to you as the very first time that the chain hits the state little x, right? So this minimum is taken over a set of times k, and the very first k, the smallest k, for which xk is equal to x, we're going to assign to the random variable tx. And of course it's random because there's no guarantee that the chain always hits the state little x at the same time 5, right? That could happen, but it could happen that it reaches state little x much later, or maybe before, right? And so this gives some randomness to tx. And so once we have that definition, we can go through these two kind of further definitions here. One is RhoX, and then similarly mx. So let's go through RhoX first. So RhoX is just this notation that I've decided on. And the equality with the triangle, as before, it means that I'm defining something. So RhoX is, we don't know what it is up to now, and now I'm defining it by this probability. And this is a probability that says that tx is less than infinity. So tx is finite. And if you see the second line, I'm defining something even further. Right here, I'm just expanding on this subscript x that stands next to the probability. So not only am I looking for to find out whether tx is finite, I'm also starting the chain at little x. And so this really is the probability that we return to x, starting from x, of course, in finite time. That's what RhoX represents. RhoX is the probability that we return to state x in finite time, or finite number of steps. And you can, this is less important at this point, but mx is a very similar definition in terms of expected value. And here I've unfortunately flipped things around a little bit. I'll fix that in the write-up. So mx is the expected value of the return time of x, right? So we're starting again at state x, and we're looking what is the expected time at which we return, and that's going to be mx. So below, definitely read the part right below these definitions. You may be kind of a little bit hesitant to when thinking about what's a finite or an infinite random variable. So like I say there's nothing wrong with giving infinity as the value to a random variable. So here I designed the random variable y, and it takes on the value 0 with probability half, and it's infinite with the remainder of the probability, so also half. So this is a definition, and it's why is it reasonable? Well, I can literally put anything to the right of that condition, right? Y equals anything. I can make it equal to an apple, right, if I wanted to, right? I'm designing this random variable, and so whatever I put there is really up to me. The only question is whether infinity is like a thing or not. Like an apple is a thing, and 0 is, I guess, a thing, right? It's a number, whatever that is, right? So so I guess my question to you would be, if you're hesitant on putting an infinite value there, why aren't you hesitant to put a 0 there? So and maybe to kind of tie the knot on this, infinity, you can think of it as just a number that's greater than any other natural number, right? So infinity is not a natural number, but you can give it meaning by saying that it's a number that's greater than any natural number, right? And any natural number is by definition finite, right? Okay, so we can certainly have finite random variables. What would that mean? Or at least we can certainly have tx be a finite random variable. And what does that mean? That means that RhoX is equal to 1, right? So when RhoX is equal to 1, you know that, but just by simply stating RhoX is equal to 1, you're basically claiming that tx is a finite valued random variable, meaning that it, at least in this case, definitely in this case because we have discrete time, that means that tx can take on values that are natural numbers only. That's what RhoX equals 1 means. And now we can get to the definition of, the most important definition that we care about so far is the, definition of recurrency. So when is a state recurrent? Well, that's going to be true exactly in the case that we just mentioned, in the case that tx is a finite random variable, meaning that we always, meaning that we always return to x in a finite number of steps. And so certainly spend some time thinking through this. It's not a trivial set of definitions, but they are, logically consistent. And if this bothers you a little bit, that's actually probably a good sign. So if this is all sort of obvious, I would kind of encourage you to think through. Maybe it's not that simple. So again, when we call a state recurrent, if it returns to that state in a finite number of steps, as decided on by RhoX being equal to 1 or not. And when RhoX is not equal to 1, right, what do we call x? We call it transient, and that means that tx can potentially take on the value infinity with some positive probability. And in that case, the example is right above, right? So I've kind of manufactured a random variable y that takes on the value infinity with probability half. So when RhoX is less than 1, you know that that's what's happening to tx, the return time, or the hitting time, right? So it's when I say return time, I'm kind of presupposing that we've started at x, right? Tx by itself doesn't have the starting point information, right? So that's an important thing to also note. Tx is just wherever you start from, it's the very first time you reach state x, and then whenever you put a probability or an expectation around it, right? Whenever you put an initial state there, here it gains on the meaning of a return time, because we're starting in state little x. If we start in state little x and we're waiting for the first time it hits little x again, we're essentially computing return time. Okay, so I think we can hold off on these positive recurrent definitions. Essentially, with the expected value mx, you can decide if a state x is positive recurrent or not, and I'll let you read those, but it shouldn't be, here I think it should be less curious that you can, for example, have, you can have mx be finite, meaning that you return in expected, you expect to return in a finite time, right? So the expected value of the return time is finite. And you can also, have an expected return time of infinite, meaning that you're expected to essentially not return in finite time. And again, here I've provided a simple random variable that is finite, right? So y is equal to k for all, has probability 1 over k. And why is it finite? Because y is equal to infinity. If you just kind of go with the definition here, y equal to infinity, the probability that is equal to 0, right? 1 over infinity is 0, and so that ensures that y is always less than infinity, right? Every outcome is less than infinity, right? Otherwise you have 0 probability, so that doesn't count. But the expected value is infinite, right? Because you multiply k times 1 over k, you get 1, and you sum those, and you get an infinite expectation for y, even though it's a finite random variable. So now let me kind of pause here, and we're going to try to prove our first theorem that uses some of these definitions, as well as kind of introduces some new ones.